Welcome back to the course on computer network and internet protocols. So, we are looking into the transport layer and the connection establishment mechanism in the transport layer. So, in the last class we have seen that well, whenever you are setting up a logical connection between two end hosts of a network, the challenge is the delayed duplicate packets. So, the delayed duplicate packets may create a confusion during the connection establishment phase, that whether the packet that you are being received, say if you have received a delayed duplicate message, whether that delayed duplicate message is or in other words, if I say it more clearly, like whenever you receive a duplicate message, you do not be sure, or duplicate connection establishment request, you cannot be sure whether that duplicate message is a delayed duplicate of the earlier one, or the client has crashed and it has reinitiated the connection with the server, and the connection request message is coming from that one. So, what we have looked till now, that the way we can mitigate this problem is by utilizing a virtual clocking mechanism with the help of a sequence number, where we are utilizing the concept of byte sequence number, that every byte in the network will have a unique sequence number. And during the connection establishment phase, we need to generate the sequence number in such a way, so that the other end, like here in the example, the server can correctly identify from a duplicate message that whether this duplicate connection request is the delayed duplicate of the old connection request, or it is a new connection request after the client has crashed. So, to do that, it can look into the sequence number field and it can find it out, but we need to ensure here that this connection request sequence number, the initial sequence number that has been utilized for connection request, it is not going to reuse within a time duration t, which is the maximum packet lifetime in the network. So, you need to ensure that with this timeout duration t, every instances of a segment, or here we are using byte sequence number. So, every instances of a byte with a sequence number is only one such instances is outstanding in the network. There are not more than one instances of the same byte in the network. Same byte means the byte with the same sequence number in the network, which can create confusion for the other end, for the receiver. So, we are looking into this problem from the context of this forbidden region. So, what we say that whenever one connection selects one sequence number, so this particular dark black line indicates, so this line indicates the sequence number that a particular connection is going to use with the respect of time. Now, if it is using this set of sequence numbers, so every byte with that sequence number, they have a lifetime. Here this lifetime is t. So, within that lifetime, the packet or the byte can be outstanding in the network. Now, in a scenario when this connection is being crashed and you want to initialize another connection, during that time, if this region of the old connection and the forbidden region, so this region we call as the forbidden region. So, the forbidden region of the old connection and the forbidden region of the new connection, if that gets overlapped, then there may be a problem of confusion. Why? Because at this time instance, you may have two different instances of the same sequence number in the network. So, one sequence number is from the old connection, another sequence number is from the new connection. So, you can have one sequence number from this old connection, another sequence number from this new connection, and we want to avoid that. Now, to avoid that, the solution mechanism that we can employ is something like this, like either you make it separate with respect to time, that means you wait for some amount of time before initializing the new connection, such that you become ensured that this particular sequence number which was there, say this sequence number it was completely gone out of the network. So, it is like that this the same sequence number which was there for this connection 1, that sequence number had a lifetime up to here. So, that sequence number is out from the network and that cannot create a confusion anymore. So, you wait for certain duration. So, here this is the wait duration and then you initiate wait say this is the wait duration. So, you wait for this wait duration and then initiate this new connection such that this forbidden region does not overlap with each other. So, if these forbidden regions do not overlap with each other, you will be sure that there is always a single instances of a particular sequence number outstanding in the network. That is one way by shifting the connection in the time scale. Another way is to shift the connection. In the sequence number scale. So, you use a sequence number which is high enough of the sequence number that was utilized for connection 1. So, that you become sure that well the sequence number field that you are going to use for connection 2, that does not have a overlap with connection 1. So, here we are utilizing this space. So, we are making a gap in the sequence number. Such that we become sure that whatever sequence number that we are going to use, that particular sequence number has not been used by connection 1. So, these are the two feasible way of setting the initial sequence number in the network. Now, let us see that how you can handle the delayed duplicates during the connection establishment by mitigating these two problems. So, if we ensure this kind of things, now when a receiver receives two segment having the same sequence number within a time duration t, the receiver knows that one packet must be the duplicate. Say it happens that well the sequence, so you are always ensuring that within that time duration t, the receiver cannot receive a packet cannot receive two different packets with the same sequence number or two different bytes with the same sequence number. Now, if the receiver is receiving two different bytes with the same sequence number with a duration t, then the receiver can correctly decode that the second one is a delayed duplicate of the first one or the vice versa, anything can happen. You can in that case the receiver can accept one and can discard the second one that it has received. Now, for a crash device, then the transport entity that remains idle for a duration t, if you are just utilizing this time scale, time period based sequence numbering, to ensure that all the packets from the previous connection are dead. So, here actually we are utilizing the first solution that I was mentioning, that you wait in the time scale and ensure that by that time all the instances of the previous sequence number is dead from the network. So, whenever you are going to use a sequence number, there is no possibility that there are two bytes with the same sequence numbers are outstanding in the network. But this is not a good solution because you have to wait for certain amount of duration. So, for that you can also choose the sequence number in such a way, we will see that in the context of the TCP, that you can choose the sequence number in such a way, so that you are significantly high above the forbidden region of the previous one, and you can be sure that the sequence number has not been utilized by the previous connection for connection establishment. Now, the solution here is you adjust the initial sequence number properly. That means, a host does not restart with a sequence number in the forbidden region based on the sequence number it used before crash and at the time duration t. So, it is just like that. If the system has crashed, then whatever sequence number was there, the new sequence number that you are going to generate, you generate in such a way so that it is above the previous sequence number. So, we will see that how we can generate this particular sequence number. Now, there can be two different source of problems whenever there are two connections, like whenever one connection has crashed and another connection is going to use a initial sequence number field. Let me just give you one example here. So, it is just like that, one connection it has used this sequence number and then it got crashed, and this is the forbidden region for this old connection. Say I name it as connection 1. Now, say there is a second connection, the second connection say starts from here with the initial sequence number. Now, if the second connection starts from here with the initial sequence number and follow this line, the sequence number space, then this would be the forbidden region, there is no overlap, my life is happy. But if this particular new connection starts sending data at a very fast rate, so if it follows this line rather than the dotted line that I have drawn earlier, then you see that this becomes the forbidden region, and here for some packets you have a overlap. So, you have certain overlap here in this region. So, in this region there can be still the confusion about the sequence number whenever you will receive a packet, whether the packet belongs to connection 1 or this new connection 2. If you increase the sequence number space too fast, then that can become a problem. So, that is why the sequence number need to be increased at a constant rate or at a bounded rate, so that the sequence number space or the increase of the sequence number for the new connection does not overshoot the sequence number space of the previous connection, so that they do not overlap with each other. Another problem is there for selecting this initial sequence number, that data rate is too slow. If the data rate is too slow, like in this example, say the initial sequence number was used like this, then the data rate was too slow. So, it started generating the initial sequence number at a very slow rate, and after that it crashed, and the new system it just start using this initial rate, that say if I name it as connection 1, that connection 1 used, and this one as connection 2, that connection was 1 used, then again there is a possibility of having a overlap here. So, both a fast connection and a slow connection can create a problem. So, we need to ensure that the sequence numbers are always generated at a bounded rate, so that this kind of overlapping of sequence numbers between two connections does not happen. So, how will you do that? So, you can do that you can bound the maximum data rate that you can send over a transport protocol. So, the maximum data rate on any connection we bound it as 1 segment per clock tick. So, here we use the hardware clock, but only the hardware clock of my machine. So, here you will see that we do not require the synchronization of the hardware clock across multiple machines. So, the hardware clock of a single machine will serve my purpose. So, with every hardware clock tick, so the clock tick is the inter packet transmission duration. The clock ticks is adjusted based on the sequences that is acknowledged. So, TCP uses this concept of self clocking or a virtual mechanism, that whenever you received an acknowledgement. So, this is something like a mix of the connection establishment and the flow control mechanism for handling the sequence number space, that whenever you are receiving an acknowledgement, during that time you make a tick that you generate a new packet or new segment with a new sequence number. So, you ensure that no two packets are there in the network with the same sequence number. So, this also ensures that the sequence number space that do not wrap around too quickly. So, you have a finite sequence number space. In case of TCP kind of protocol, you have 32-bit sequence number. Now, if you have a 32-bit sequence number, then you can use 2 to the power 32 different sequence numbers. So, you need to ensure that this entire sequence number space does not wrap around too quickly. So, that means if you are sending data at a very high rate, it may happen that you are generating the data in such a rate that you have within that time duration t, or even before that time duration t, you have finished this entire 32-bit of sequence number space. So, that may create a confusion, because that may create a confusion. So, you want to prevent that, and to prevent that you want to regulate the sender flow as well apart from the receiver flow. Normally, with the flow control algorithm, we coordinate between this sender flow and the receiver flow, but whenever we are generating the sender packets, we also want to ensure that the packets which are being generated from the sender, they follow certain kind of I will not say it is a constant rate, rather within a bounded rate. So, so that is why the application is generating data as its own rate, and the data is being buffered at the transport layer buffer, and the transport layer picks up the packet from there, picks up the bytes from there, and generate the segments with a predefined bounded rate, so that the sequence number space does not get overlapped with each other. So, we will look all this mechanism in details. For the time being, it may be little unclear, or you may have a little bit doubt. That things will be much clear to you whenever we look into the flow control algorithms in details, where we will look into that how flow control actually helps in adjusting this entire sequence number space. Now, the second thing is that if you remember that the Tomlinson's proposal, that our first requirement was to have a way to selecting the initial sequence number. So, here what we want, that we do not want to remember the sequence number at the receiver side. So, the receiver does not want to remember the old sequence number, rather the sender will manage its own sequence number. So, for that we use a three-way handshake mechanism to ensure that the connection request is not a repetition of the old connection request. Now, the individual peers, they validate their own sequence numbers by looking into the acknowledgement. So, this provides the positive synchronization among the sender and the receiver. So, let us look into how this three-way handshaking works. So, whenever host 1 is sending a connection request message, host 1 sends a sequence number value x. So, here host 1 sends a sequence number value x, and host 2, it sends back with an acknowledgement. With the acknowledgement, it also puts that sequence number x, and it also, so in case of transport layer, normally our connections are bidirectional. Because the connections are bidirectional, with this particular acknowledgement, the host 2 also sends another acknowledgement, sends another sequence number for reverse connection from host 2 to host 1, that is the sequence number y. Now, whenever the host 1 receives an acknowledgement to its sequence number x, host 1 can verify whether this sequence number which was there in the acknowledgement, it is the original sequence number or not. It is the sequence number of the connection request message that is sent, it is correspond to that or not. If it is okay, then it can send the data with that sequence number x, and at the same time it can also send acknowledgement for the sequence number space or the sequence number that was proposed by host 2 for host 2 to host 1 data transfer. So, this three-way handshaking ensures that all the delayed duplicates are correctly identified by both host 1 and host 2. So, let us see that how with this mechanism they can correctly identify delayed duplicate of the sequence numbers. So, let us see a case when the connection request is a delayed duplicate. Now, if the connection request is a delayed duplicate, so the host 2 has received a delayed duplicate connection request with a sequence number x. So, it sends back with an acknowledgement of that x. Now, host 1 can verify that this particular acknowledgement that it has received, it is not for a connection request that it has sent. So, that connection request was a old duplicate that it has sent long back, and now host 1 do not want to use that connection anymore. Maybe host 1 has crashed here and then it got restarted here. So, it do not want to use that old connection request that it has requested earlier. So, host 1 can find it out, and if it finds out that this acknowledgement is a acknowledgement the sequence number field which is there in the acknowledgement message, it is for a delayed duplicate, then it can send a reject message. By looking into the reject message, host 2 can identify that the connection request that was sent that it has received, it is not going to be accepted by host 1 anymore. So, there is no point in establishing the connection. Now, let us look into another case when both the connection request and the acknowledgement are delayed duplicates. Now, when the connection request is a delayed duplicate and host 2 sends back an acknowledgement here with this sequence number x, which it was received as a part of the connection request message, and it proposed with a new sequence number y. During that time it gets a reject message, but for the old duplicate that it has sent, say it has received one acknowledgement here, this acknowledgement says that it is a sequence number for x, but the acknowledgement number says that well the acknowledgement number is z. Now, if you look into this three-way handshaking mechanism, this acknowledgement number should correspond to the acknowledgement number should correspond to the sequence number that was proposed by host 2 in its acknowledgement. Now, these two are not matching, so host 2 will reject this duplicate acknowledgement. At the same time, host 1, whenever it has received this acknowledgement message and it finds out that it do not want to use this acknowledgement x anymore because it has crashed here and say restarted here, then it can send a reject message. So, with this way you can identify that both the connection request was a delayed duplicate that was identified by host 1 and it sends a reject message, and host 2 whenever it looks a different acknowledgement number, acknowledgement number z compared to the one which it has sent with its own acknowledgement, whenever it finds out that there is a mismatch here, it simply discard this acknowledgement. So, that way you can properly differentiate between with the help of this sequence number between the normal connection request messages and delayed duplicate connection request messages. Well, so that was all about the connection establishment. So, what we have broadly seen here, just to give you a summary of the entire procedure, the connection requesting. So, what we have seen that because packets can get dropped in a packet switching network, there can be arbitrarily delay in transferring the packet, there can be loss. Because of this reason, there is always a possibility of having a delayed duplicate. Now, what we have learned till now that my major problem is to select the initial sequence number for connection establishment. Once this initial sequence number is established, then the flow control algorithm takes care of maintaining the sequence numbers for the data packets that we will look later on, that how flow control algorithms actually helps you to set up the sequence numbers for the data packets or the data segments in the context of the transport layer. But the challenge here is to select the initial connection request in such a way, so that you can ensure that the forbidden region of a new connection does not get overlapped with the forbidden region of an older connection, where both the new connection and the older connection are initiated on the same application at the same source destination pair. So, they are likely to use the same port. So, in that case our objective is to separate out a normal connection request from a delayed duplicate connection request, and in that case we take the help of a sequence number. Now, we have looked into that how to choose an initial sequence number, but whenever you are choosing the initial sequence number, you have to ensure that well your initial sequence, the sequence number field does not increase too fast, or too slow such that it gets overlapped with another connection. In that particular context, this rate of control of sequence number, that is taken care of by the flow control algorithm, and we ensure that well the packets are generated or the bytes are not, I will not say generated, but that the transport layer transmits the bytes, transfers the byte in such a rate, so that it is not too slow or not too fast. All the connections follow almost a bounded rate. But whenever you are selecting the initial sequence number, you can use this three-way handshaking mechanism for selecting the initial sequence number, such that even if your connection request is a delayed duplicate, or the connection request or the corresponding acknowledgement is a delayed duplicate, you will be able to differentiate between the old connection and the new connection by ensuring that the sequence numbers are not generated from the forbidden range of the previous connection, and you are making sure that no two bytes in the networks are having same sequence number between the same source destination pair coming from the same application at the same time instance. Now, let us look into the connection release. Connection release is little bit easier compared to connection establishment, because we do not have the problem of sequence number here, but here we have a different problem. So, there can be two type of connection release. One we call as the asymmetric release. So, the asymmetric release says that when one party hangs up, the connection is broken. Now, it is just like that whenever host 1 is ready to or whenever host 1 is done transferring the data, host 1 breaks the connection. Say it may happen that host 2 now wants to close the connection. Host 2 simply sends a connection release message. So, here it is DR, data release message. Host 2 sends a data release message and host 2 goes to sleep. Now, even if host 1 has some data to send to host 2, that particular data, even if host 1 has sent it, host 2 may not be able to receive that data. So, there would be a possibility of data loss. So, it is a concept of asymmetric release. Now, we can have another variant of this connection release, which we call as the symmetric release. Now, in case of symmetric release, you treat the connection as two separate unidirectional connection. Every individual connection is treated as two separate unidirectional connection, and it requires that each one to be released separately. So, when both one is released the connection, then the final connection will get released. Now, this is good when this particular symmetric release is good when each process has a fixed amount of data to send, and it clearly knows that when it has sent it. So, it knows, it has an idea that when it has sent that particular data. But the question comes that can we design a protocol for this symmetric release. So, let us look into a very simple protocol that host 1 will say that I am done, host 2 will say that I am done too. So, when both are saying that I am done and this one is saying I am done too, they will release the connection. Let us see that whether this protocol works good always. So, we map this protocol in the context of a problem called two army problem. So, we have a white army which is there in a valley, and the blue army which was there in the hill. Now, you see that the total fighters in that blue army, it is more than the white army, but they are separated out, they are in the two part of the hill. So, they need to communicate with each other to make sure that both of them attack simultaneously. Both of them are able to attack simultaneously, then they only they will be able to defeat the white army, otherwise they will not be able to defeat it. Now, the problem here is that if the blue army wants to send a message called attack, this blue army 1 wants to send that message to blue army 2, they have to go via the valley, which is a vulnerable position. So, it may always happen that one soldier of white army is able to see that soldier of the blue army and kill that person, and the message is not delivered in the other way. So, the environment is unreliable. Now, whenever the environment is unreliable, you can see that you will never be able to make a protocol, correct protocol to solve this particular problem. that both the blue army will come into consensus and they will be able to attack the white army simultaneously, because whenever you are sending one soldier of blue army via this valley, blue army 2 may not get that particular soldier message from that particular soldier, and they will not be able to sure whether to make an attack or what is the current condition. So, we cannot have one protocol to solve this particular problem. So, in this case the best way you can do is that let every party take their independent decisions. So, that is the protocol we implement here, that every individual host. So, host 1 it will send a data release message and then it will start a timer. Similarly, host 2 it will send the data release message and it will start a own timer. Whenever it is receiving the message from host 2 within this timeout value, it will release the connection and it will send the acknowledgement, and if host 2 is getting this acknowledgement message within this timeout value, it will release the connection. Now, let us see that how this protocol works when the acknowledgement is lost. If this final acknowledgement is lost, say this final acknowledgement is lost, if this final acknowledgement is lost, then this host 2 it has started this timer after sending the data release message, it will not get the acknowledgement. So, it will wait for the timeout value. Whenever the timeout will occur, it will release the connection. Then say this particular data release message from host 2 got lost. So, if this data release message from host 2 got lost, so here host 1 has sent a data release message which host 2 has received and host 2 has sent another data release message. So, host 1 will get a timeout. After it will get a timeout, it will again send the data release message. So, once it is sending a data release message, host 2 will receive that message, it will again start the timer, send the data release message. So, once it is getting this data release message, it will release the connection, send the acknowledgement, and once host 2 will get that acknowledgement, it will release the connection. Now, let us see another scenario when both the data release and the acknowledgement are lost. So, here this data release is lost and as well as the acknowledgement is lost. In this case, so if both these messages are getting lost, then both the node will wait for a timeout value. So, here you can specify that host 1 it will try for n different timeouts, and once this n different timeout occurs, it will release the connection, and host 2 it will wait for similarly for the timeout value. Once the timeout occurs, it will release the connection. So, here we are basically making the protocol from a asymmetric view, that we will wait for certain timeouts, and if you are not able to solve the problem with that timeout value, then you independently release the connection. But as we have seen earlier, in case of asymmetric connection, there is always a possibility of having a data loss. So, this particular lecture, it has given you the idea about the first services, first of the services which is being supported by the transport layer of the protocol stack, where we need to establish the connection between two remote hosts, which is a kind of logical pipe to establish the hello messages between the two ends. And because of this reliability problem in the network, we see that ensuring the connection establishment is a challenge. You can argue that, well, I have the reliability protocol, then why I should bother about all these difficulties during the connection establishment. But you remember that the reliability only comes that when you have set up this initial sequence number. So, then you can apply your flow control and the reliability protocol, which we will look later on. We call them as the automated request protocol, ARQ protocol. So, this ARQ protocol, they can take care of the loss by retransmitting the packet, because they have a reference frame through which it can utilize the sequence number field. But whenever you are setting up the initial connection, during that time you do not have any initial reference frame, like from where you will start the sequence number. If every connection starts from sequence number 0, then that can be a problem, because of that forbidden region concept that we have looked earlier. Now, to solve this particular problem, we have seen that well, by utilizing this self clocking mechanism through the hardware clock or by clocking from the acknowledgement, you can generate the sequence number fields, ensuring that the sequence number of a connection for the same source destination pairs with the same port, they do not overlap with each other, and at the same time you are ensuring the sequence number in such a way it should be higher enough from the previous sequence number, so that they do not get overlap. And finally, once this sequence number is established through this three-way handshaking mechanism, and during that time we have seen that if there is a loss or a delayed duplicate of the messages, the other ends will be able to correctly decode that. In the context of connection release, we have seen that well, a symmetric release is a good option, but asymmetric release is a good option, but you cannot design a protocol for asymmetric release in a unreliable channel. So that is why we go for a symmetric release with a timeout value. So you will try to make a symmetric release. If you are not able to do that within certain number of timeout, then you forcefully close the connection. There is always a possibility of data loss, but as I have mentioned earlier, there is always a trade off between the performance and the correctnness. So here we are not going for a protocol which will be completely correct. There can be certain amount of data loss always due to this symmetric release mechanism, but our target is to minimize it as much as possible by utilizing that timeout value. The timeout ensures that whatever packet that has been sent by the other end, that will reach at the destination within that timeout value. So that is all about the connection establishment and connection release. In the next class, we will look into another service in the transport layer. So thank you all for attending the course.